Today I'm going to talk to you about independent events. To do this, we're going to consider tossing two coins. So let's look at the first coin by drawing a tree diagram. If we throw one coin, we know the probability of getting a head is a half, and the probability of getting a tail is a half. Let's look at the second coin. When we throw the second coin, we get a head and a tail. We know here that because this is not related to this coin, we're throwing it again, the probability is still 1/2. And again, obviously, if we're following down this path, we have the same options. Now, what we understand is that this probability here, all these probabilities down here, are following a path where there's a given condition. So this is actually the probability of getting ahead, given the fact that we got ahead on the first throw. Let's look at this one, for example. This probability here is actually the probability of getting a tail, given the fact we got a tail on the first coin. Now I could write the same on each of these as well. You'll notice that when we do tree diagrams, we often want to know all the possible outcomes. So if we have a look at multiplying the probabilities, so head and a head, we are looking at the probability of head intersection head, which is 1/4. And we can look at the intersection of all of these, and it gives us 1/4. Now what's interesting to notice about these two events that I'm talking about, so throwing the coin, is this here, all of these here, these given conditions. Now, we also know from the conditional probability video that there's a formula for given conditions. So if we want to use the formula for probability and conditional probability, we know that that is the probability of getting ahead and ahead divided by the probability of getting ahead. So let's have a look what that would come out of using the numbers on here. Probability of head and head is 1/4, divided by just the probability of getting ahead, which is a half. 1/4 divided by a half is 1/2. So by using the conditional probability formula, we've found that the probability of getting ahead given a head is a half. But we also know that this also shows the probability of head given a head. Because the two equal each other, these two events are said to be independent. What that means is that there's no relation between what happens on this coin and what happens on this coin. And we have just proven this by using the formulas that we know. So from the last example that I just did, because we knew that the probability of a head given a head was a half, and we proved that in two different ways, we also understand that the probability of a head is a half. These two things are the same, which means they are independent. Now I'm going to generalize this using some formulas. So I'm going to use A and B. So I'll just rub this off. Alright, so generalizing. If two events, say A and B, are independent, what this means is that the effect of one has no effect on the other. So the occurrence of one doesn't have any effect on the other one. And what we just proved on the last example was that the probability of A given B was the same as the probability of A. Obviously, I used the probability of a head given a head was the same as the probability of a head. So we've just discovered that. Now, we also know from conditional probability, so we'll call this one equation 1. We also know from conditional probability that the probability of A given B is the probability of A intersection B divided by the probability of B. Now, let's call that equation 2. Now, because they're both equal to the same thing, let's equate them. So we can put the probability of A equal to this. So the probability of A equals the probability of A intersection B divided by the probability of B. And we can rearrange this. If we rearrange this formula and bring this up here, we can say that the probability of A intersection B for two independent events A and B is the probability of A multiplied by the probability of B. During the exercise that you work through, you will be using all three of these formulas, rearranging them, manipulating them to find certain aspects. I'll run through one example in a moment. So I'm going to do this quick example where we want to know whether A and B are independent events. So let's have a look first of all. Let's look at the probability of A. The probability of A is 1, 2, 3, 4 out of 8 numbers. So 4 out of 8, which we know cancels to 1/2. Let's look at the probability of B. Probability of B is 4 out of a total of 8, which is 1/2. Now, let's look at the intersection. The intersection of A and B is just this section here, which is 2 out of 8. So we found that from the Venn diagram, which is a quarter. Now, if A and B are independent, when we multiply them together, we should get this number here, if they are independent. So let's try it. Let's look. If probability A multiplied by the probability of B is 1/2 times 1/2, which is a quarter. Oops. Because we know this relationship would equal the intersection, and we see from the Venn diagram that it's a quarter, these two are equal. So yes, we can say that A and B are independent events.